Okay, today I'd like to do something a little different. I'd like to introduce you to a very famous statistician. His name is Hirotogu Akaike. And his picture is shown below me there. He was famous for coming up with the Akaike information criterion. And he used information theoretic approaches, maximum likelihood, and Bayesian approaches to trying to come up with an objective way to decide between model fits. And the basic notion of Akaike's information criterion is that by continually adding parameters to the model, we will always fit a little bit better, but we are also trading off against overfitting and actually losing information about the real underlying pattern. So it represents a trade-off between the number of parameters you add and the increase or the incremental amount of error that you're accounting for by doing so. And so last I checked, the original AIC paper was cited more than 22,000 times. That's incredible. It's an incredibly high citation rate. So kudos to Hirotogu Akaike. He died, by the way, in August 4th, 2009. He was known as a very humble man, never satisfied with the research career that he had, his contributions. He always was trying to do more, apparently even in the hospital. As he lay dying, he was continuing to work, and he's been honored in Japan and worldwide for his contributions. But particularly the Akaike information criterion has really proliferated across many, many disciplines in terms of model selection. So how are we going to use it? The way we use it is to decide between, for example, different regression models that we might want to try to explain the relationship between y and x. So how do we do that? Well, we don't actually do the mathematics, but I'm going to quickly show you that AIC equals, and this is a simple formulation of it, there's a likelihood formulation which you can read. N times the log of the sums of squares, and this is the error sums of squares that we're talking about, divided by n plus 2k, where n is the number of observations, k is the number of parameters that we have fit plus 1, okay? And then, as I said, S is the sums of square error for the model. Okay, and so I'm going to give you an example of some kind of numbers we might get. For example, if we try a certain set of data and we try a linear fit and a polynomial fit, I'll show you just some actual numbers from a real regression that I tried recently. The n in both cases was 20. K was 3, so in the case of the linear fit we have A, B, and then we add 1 to that, so we have 3 parameters, or 3 is the value of K, 2 parameters. And then the polynomial was a second order, so we have A, B, and C, which we're estimating, and we add 1 to that, so it's 4. And then the sums of squares for the error in this particular regression was 122 for the linear regression, and notice it got smaller for the polynomial regression. And by the way, it almost always will. So every time we add parameters to a model, we'll explain a little bit more because a curved line can fit points generally better than a straight line, and if we allow for inflections, that can fit better than a simple curved line. Okay, so if we apply Akaike's information criterion to this, we get an AIC value of 156.17, and for the polynomial regression we get 0.86. So the question is, what do we do with these numbers? Well, it turns out the model with the better fit has the lower AIC value. Okay? So most statistics packages, including SASJump, can calculate this AIC value for you. In SASJump, it's kind of hidden in the fit model platform, so you won't find it, I don't believe, in fit y by x. But if you look under fit model and you do the fitting there using our general linear model approach, you'll see under one of the tabs it has an AIC value. And we would then identify by trying these two fits that the linear fit is the more appropriate fit in terms of containing information and not overfitting our data. Okay, JUMP also provides you with a BIC, which is a Bayesian information criterion. And I believe, from what I've read, that the Bayesian information criterion penalizes the number of parameters, even more than AIC. In other words, it emphasizes simplicity in the models. Okay. Also, depending upon the sample size, you may need to correct the AIC value, and you'll see a little subscript, AIC corrected. So these are two objective ways of deciding on a model that is most appropriate in terms of having enough complexity that it accounts for additional variation in Y, but doesn't overfit the model as well, given your sample size and given the sums of squares error. Right? So, Hirotogu Akaike, famous man. It sounds like a guy would have been fun to have dinner with sometime. All right. Take care.